So last week we started our linear programming unit, and we were looking at problems like this. So we wanted to find the values of x1 and x2, which were non-negative, that satisfied some constraints and that maximized a certain quantity. So typically we're going to write z for the thing that we want to maximize, and we'll have some set of constraints that we need to be following. So the strategy that we took last week was the graphical strategy. The idea was that we would take these constraints and the non-negativity constraints, and we would graph them to find the so-called feasible region. So we would find a little region like this that satisfied all of those inequalities. And then we knew that this linear function, the objective function, was going to be maximized at one of these corners. So last week we just plugged in all of the corners and we saw which one of those corners optimized z. And in this week we're going to continue solving problems of this type, but this time we're going to do a more sophisticated approach. So this time we're not going to be graphing anything. Now we're going to move on to using matrices. So I think I want to continue using the analogy between Unit 3 and Unit 4 that I've mentioned already, which is that in Unit 3 we started working with systems of equations, and we started by taking a system of equations and translating it into a matrix. We also learned how to take that matrix and translate it back into a system of equations, and then we learned a bunch of row operations that we could do to solve that system of equations using matrices. And our approach here is going to be very similar. So in Unit 4, well, in this lecture, I will start by showing you how to take a setup like this and turn it into a corresponding matrix. That'll be our first step. Our second step will be to take that matrix and translate it back into a solution for the problem of this type. So we'll learn how to interpret a matrix. And then our third step, which will be in the next video, is what row operations you need to do in order to get from the initial matrix to the final matrix, where we can just read off the final solution. So that's what we're going to do here. There's sort of good news and bad news about this section. The good news is that these problems are very algorithmic in the sense that you just have step-by-step processes for solving all of these problems. So notice that here, this is the initial setup for the problem. There's just a bunch of steps that we're going to go through to set up these problems, and you'll have access to these. Remember that the quizzes and exams are open note anyway, so you can just have these in front of you. You don't really need to memorize anything. The bad news is just that there's a lot going on here. So that's why I want to break these up into some smaller sub-problems at the beginning. So this first page is mostly review of what we talked about last time. In linear programming, you're trying to optimize some objective function subject to some constraints. The method that we're going to talk about today is called the Simplex Method. The reason it's called the Simplex Method is because the picture that we drew last week, this shape, this polytope, is sometimes called a simplex. And the idea here is that we're going to be using matrices to check all of these corners until we find the optimal one. And I'll comment a little more on that later. So for this, it's important that we have our linear programming problem in standard form. And the rules for a standard form problem are these three rules. Z will be the function we want to maximize. And then all of our variables, x1 through xn, are constrained to be non-negative, like we saw a second ago. And we also want all of our constraints to be something involving your variables on the left side is less than or equal to, and then some non-negative constant on the right side. So those are the rules for a standard form for this linear programming problem. We'll see next week how to solve non-standard forms of linear programming problems. But for today, all of the problems that we're going to look at are going to be of this form. And by the way, it's typical to have more than one or two variables that we're going to be using. So instead of calling them x, y, z, and so on, and maybe running out of letters, we're normally just going to call our variables x1, x2, x3, and so on, so that we can use as many of them as we want to. So you can check that this linear programming problem that we have here is in standard form. So we're trying to maximize this function z, which is a linear function of our variables. We have our constraints in standard form, and all of our variables are constrained to be non-negative. So the first idea that I want to talk about is with all of our matrices, we've been taking equations and translating them into a row in the matrix. And the same thing is going to be true here. So the first issue that we have is that matrices don't like inequalities. They would prefer to have equalities. So we want to convert these two constraints into equations. And the idea for doing that is that we can convert these into equations by introducing what's called a slack variable. So by the way, I'm going to go a little bit quickly through these because I know that you can sort of read them in your own time. But if you'd like, you can pause the video as we get to new pages and just read over or scan over the page before I get to it, if you think it would help you to read all of the details here. But here's the idea. We're going to take something like that first inequality that we have above, and we want to translate it into an equivalent equation. So maybe, just for the sake of example, this is saying that x1 plus x2 plus x3 needs to be less than or equal to 10. So maybe let's say that x1 plus x2 plus x3 ends up being not equal to 10, but instead it equals 7, something a little bit less than 10. We can still take this inequality and turn it into an equation by just adding what's called a slack variable. And that slack variable would take up the slack between this left side of the inequality and 10. So in this example, I would have s equals 3 if the sum of those three variables were 7, and then I've translated this into an equivalent equation that just involves this slack variable. And notice that the slack variable is also going to be bigger than or equal to 0. That's because the left side is a little bit smaller than the right side in this initial inequality. So that's how we're going to translate our constraints into these equalities by introducing a slack variable. And we're going to need to introduce a slack variable for each constraint that shows up. So each constraint will have its very own slack variable. So that's what we're going to do, and then we'll be able to write down the initial matrix. Here, there's a fancy term for the initial matrix. I'm going to call it the initial simplex tableau. So a simplex tableau is just the matrix that corresponds to a linear programming problem. So we want to compute the initial simplex tableau, or the initial matrix that corresponds to this problem. And here are the steps for doing that. Again, if you'd like, you can pause the video and read over this, or I would recommend just having the notes open in a separate tab so that you can sort of scroll through them as I go through this video. So step 1 is just to add a new slack variable to each of the constraints like we had a second ago. So notice that for the two constraints that I have up here at the top, for these two constraints, I can turn them into equalities by just adding a slack variable to each. And notice that the slack variables, because I need a new one for each inequality, I'm just going to call them S1 and S2. And we would continue with S3 and S4 if we had 3 or 4 constraints. The non-negativity constraints, these down at the bottom, those are never going to go into the matrix. Those are implicitly going to be satisfied by the method that we use for this problem. So you can basically ignore this non-negativity constraint, but it is important in that it is implicit in what we're using for our solution strategy. So that's step 1, is just add your slack variables. Step 2 is to translate those equations that we have up here into corresponding rows in a matrix, in an augmented matrix. This is exactly the same as what we would do for solving systems of linear equations. So the translation method is exactly the same. You just record the coefficients on each of the variables. But here, excuse me, here there's a slight difference in that, well, I don't know if it's really a difference, but what I'd like for us to do is record all of the variables that we started with at the beginning, so x1 and x2 in this case, and then record your artificial variables or your slack variables, and then we'll record the coefficients on z, and then we'll record the constants that are on the right side of the equal signs. So that's going to be the general format for setting up the columns in these matrices. So that these two lines or these two rows came just from the constraint equations. And then there's going to be one more row in our matrix. That row is going to correspond to our objective function row. And here what we want is we want the coefficient on z to equal 1, but we also want to collect all of the variables on the left side so that we just have a constant on the right side. So notice that up here we had the the objective function z is equal to 50x1 plus 80x2. What I would do here is I would move both of these over to the left side of the equation so that my right side is just a constant. So I would subtract 50x1 and I would subtract 80x2 from both sides of that top equation. And that would lead me to this equation here. And then this is the equation that I would actually record down here in the bottom row of the matrix. So that's what we get as our bottom row. The bottom row is always going to correspond to the objective function. And this is the initial simplex tableau. So there are a couple of other terms that I'm going to introduce now, but we'll talk more about them in a second. The first term that I want to introduce is the idea of an indicator. These numbers that I've just circled are the indicators. They're the coefficients that live to the left of the augmentation bar. So it's all of these. And our goal is going to be to eliminate any negative indicators. So we'll be done as soon as we get rid of all of those negative indicators. In this case, there are two negative indicators. There's negative 50 and negative 80. So our goal will be to eliminate those negative indicators, and then we can read off the optimal solution, but we'll worry about that in a bit. And then the last term that I want to introduce is called pivoting. That we'll talk about in our next video. Excuse me. So pivoting we'll go over in our next video. That's just the row reduction process. So those are the steps that we'll take in order to get rid of those negative indicators. Okay, so that's the basics for just setting up the initial simplex tableau. Let's do an example involving this setup. So here it says introducing slack variables is necessary, write the initial simplex tableau. So our first step is just going to be to take this set of constraints and we're going to turn them into equations. And I do that by just adding a slack variable. So I'll add S1 as my slack variable for that top constraint, and I'll add S2 as my slack variable for that second constraint. And now I've converted our constraints into these equalities. And that's enough for us to start setting up the initial simplex tableau. If you would like, you can start labeling the columns here, just to make it clear what the individual columns represent. But you don't necessarily have to label the columns. So it's okay with me if you omit the column labels. But they should always just be your initial variables in a row, and then your slack variables in a row, and then your z coefficients, which will only really show up in the objective row, and then the constants on the right side of these equations. So first, let's just put in our two constraint rows. So we'll have the coefficients 4, 2, 1, 0, 0, 5, if I just translate this top equation. And then the next row would be 1, 2, 0, 1, 0, 4. Notice that here this 1 belongs in the S2 column because it has its own slack variable. This is not going to also correspond to the S1 slack variable. So basically this portion of the matrix should end up being diagonal ones, because we're introducing a new slack variable for each constraint that we have. So those are the two rows that correspond to the constraints. And then lastly, if I want a row that corresponds to the objective function, then normally I like to put a dividing bar here again. So I would put a little bar here like we did for the augmentation column. And remember that we need to rearrange this so that we have a 0 on the right-hand side and all of our variables over here on the left-hand side. So if I rearrange, this would become a negative 7x1 minus a 2x2 plus a z equals 0. So that's what we get whenever we rearrange our objective function. And whenever I translate that into the corresponding matrix row, I would get a negative 7, a negative 2, 0, 0, 1, 0. So this thing is our initial simplex tableau. And if you'd like, you can extend these so that they sort of come down like this. But that's our initial simplex tableau. And notice here we have two negative indicators. There's the indicator -7 and the indicator -2. Our goal will be to eliminate those as soon as we can. But this is at least the initial simplex tableau. So if I ever ask you just for the initial simplex tableau, then your answer would be this. You don't necessarily need to be able to solve this, this problem. Okay, so the next page in the notes is about pivoting. So I want to postpone this for the next video. So don't worry about pivoting quite yet. That's just the row reduction operations that we're going to be using in order to solve these problems. But what I want to discuss lastly in this video is how to read a solution. So let's say that I tell you that this is the final simplex tableau that we have. We need to be able to translate this back into a solution that applies to our original problem. So now we're going to talk about how to read the solution. The idea here is this. So I want to translate this matrix back into some equations. But in order to do this, there are some columns that I want to ignore. So step one is to identify which columns are basic and which columns are non-basic. In other words, which of these variables are basic and which of these variables are non-basic. So what I mean by basic or non-basic is if you have a variable whose column is just a multiple of a column from the identity matrix, or equivalently, a column that has only one non-zero entry, like this one, and this one, those are going to be called basic variables. So we like those. So we want the columns that have just a single non-zero entry. Those correspond to basic variables. If you look at a column that has more than one non-zero entry like these, those are columns we want to ignore. So those are called non-basic variables. And we will ignore those. Typically what I like to do whenever I'm reading the solution is if you have a non-basic variable, then I would just scratch out those columns from the matrix because they have too many non-zero entries. So step one is just to identify which ones are basic and non-basic. Here, the two scratched out columns correspond to non-basic variables. And in the solution that we would read off from this matrix, those two non-basic variables would just be set equal to 0. So here x2 and s1, those are both going to be 0. So in other words, when you scratch out a column, that just means that the corresponding variables are 0. And lastly, to read off the values of the other variables, we just take the matrix that remains, so ignoring these two columns, we take the remaining matrix and we translate it into equations like we would with systems of equations. So notice that if I look at the remaining top row, it would say that S2 equals 32. If I look at the next row, it would say that x1 is equal to 84. And if I look at this last row, it would say that 2z is equal to 4. And that's how we interpret this matrix and find the values for all of the variables that it's suggesting. Okay, so that's how we are going to read these matrices. I'm actually going to delete this note because I don't want these columns to be occluded. So I want us to be able to read these columns whenever you look back over the notes. But the general strategy is written up here. I'm going to continue scratching out these variable columns that correspond to non-basic variables, just because I think it makes it a little bit easier to read those values for the other variables. So step 4 is going to be to solve for these individual variables if you need to. So notice that here we can just read off x1 and s2. In this last equation, we would need to divide by 2. But most of the time, we'll be able to just read off the values of these variables. So this would say that x1 is 84, s2 is 32, and z is 2. And notice that you can do this for any matrix that looks like this. So for any simplex tableau, you can always just interpret it and read the values of each of the variables. Any non-basic variables will be set to 0. Any basic variables, you can just translate that line and get the values for those variables. So you can do this for any matrix, so any simplex tableau that we work with, even the initial simplex tableau. But there is something important, which is that we need to be able to decide which matrix we should read off in order to get the actual optimal solution. Because notice that here I could read off, maybe just for practice, let's read this one off. So notice that here x1 and x2 are non-basic because they have too many non-zero entries. So I would have x1 equals x2 equals 0. And then I would have s2 equals 5. Sorry, that's s1. s1 equals 5, s2 equals 4, and z equals 0. So what this is saying is that if you drew the initial feasible region like we did last week, this initial simplex tableau is starting at the 0, 0 corner, and we're getting a corresponding z value of 0. And these slack variables were just invented to take up the slack. So you can think of them as not really being part of the solution. We invented them as a convenience for applying this method. So this simplex method is going to start down here in the 0, 0 corner, and then it's going to traverse these different corners until it finds the optimal solution. So notice that here, if I just read this matrix and interpret it, I'm not going to be reading off the optimal solution. Z equals 0 is not the optimal z value. So how do we know when we found the optimal z value? That's part of step 5 here. It says if all of the indicators are non-negative, then we do have the optimal solution. So ordinarily we want to wait until we have none of the negative indicators remaining. So once all of the negative indicators are gone, then we'll read off the solution and it will be the optimal solution. So if we look at this example, there are no negative indicators, and therefore if we just read off the matrix like we did a second ago, this will represent the optimal solution. And that means that the optimal z value that we could get for the corresponding linear programming problem here would be a z value of 2. Right, so the optimal z value would be 2, and it happens when x1 is 84 and when x2 is 0. And again, you can sort of ignore the slack variables. We just sort of made them up so that we could apply this method. So as our last problem in this video, let's just read off the solutions for this simplex tableau and then decide whether these represent the optimal solution. So first I'm going to eliminate the non-basic columns. So this column, this x2 column, should be eliminated because it has more than one non-zero entry. The same applies to this column and this column. So I'm going to eliminate those columns. And now all of the columns that remain are basic. By the way, if you end up having two columns, so maybe let's say you have x1 and x2 like this, and then over here you have a C of 7, 0, 0, for example. If you have a repeat of the same basic column like this, then you wouldn't read this as x1 equals 7 and x2 equals 7. If you have a collision between the columns, then we're just going to delete the second one. So we don't want two basic columns that have the same non-zero entry. So that's just sort of a subtlety here. If you had the matrix that I just wrote down, you would translate it as saying that x1 equals 7 and x2 equals 0 because it has the same entry that we already used in a basic column, the same non-zero entry. So that's in the instructions up above. It says, so let me see. Yeah. So it's part of this step 1. If two variables columns are multiples of the same column, then we're only going to take the first one, and the other one would be considered non-basic, so we would scratch it out. but I don't think we're actually going to see any examples of that in the notes. It's pretty rare for that to happen, but just be aware of that technicality. So returning to this one, we'll scratch out the non-basic columns. And remember, that means that those variables are equal to 0. So if you'd like, you can immediately write down that those 3 variable columns that we scratched out correspond to zeros. And now we're going to translate the rest of them. And you can decide which variable you're interested in first if you'd like. So for example, if I wanted to know what x1 was, then I would go to the entry in x1 that was non-zero, and I would translate that row into an equation. And if I ignore these scratched out columns, then what I would have is 7x1 equals 35. And I can do the same like this. So let's say I want to know x3 now, then I would be translating this row, because that's the x3 entry that's non-zero, or that's the row that has the non-zero x3 entry. So this would say x3 equals 2, and then we have 5s1 equals 15, and then 2z is equal to 40. And by the way, for a lot of these, you can mentally just compute the values of the variable. I'm okay with that. So for example, instead of writing 7x1 equals 35, I would be okay with you just immediately writing that x1 is equal to 5. If you can just see that by staring at this row, then that's fine with me. So you don't necessarily have to write down 7x1 equals 35. You could just divide that entire row by 7 to get the appropriate x1 value. Here we have x3 is equal to 2. We have s1 is equal to 3, and z is equal to 20. Now it's typical whenever we write down these problems solutions, it's typical for us just to report the initial variables that we started with, so x1, x2, x3. And then z, which is the value that we wanted to optimize. We normally don't include the slack variables unless we especially need to. That's because we basically invented the slack variables just in order to be able to solve the problem this way. So the only variables that have meaning in terms of the original problem for now are just going to be the variables that you started with, x1, x2, x3, and then z, which is what we're trying to optimize. And then lastly, to answer this question, are these solutions optimal? The answer is no, these solutions are not optimal. I've sort of covered it up, but there is a negative indicator here. There's a -4 as the indicator. So there is a negative indicator. And therefore, this solution that we've just read off would not actually represent the optimal z value. So we should be able to do better than z equals 20. And in our next video, we'll talk about how to go from this matrix to a matrix that has a better z value.